So from this equation, just write this denominator. This is 1 upon C upon M into D plus this is K upon M minus omega square. Okay, so it is the same equation. Just we have written K upon M minus omega square in bracket and into sine omega t. Okay, so now our aim is we should replace this d from the denominator. Okay, but as per this standard equation or a standard rule, we can only replace a d operator if there is a d square term, and therefore we need to bring that term in this equation. So we should multiply and divide this complete equation by the conjugate term of the denominator. Okay, so multiply and divide this equation by C upon md minus this bracket. Okay, so the x particular integral, this is equal to f0 upon m 1 upon C upon m into d plus K upon m minus omega square now multiply by the conjugate of the denominator. So it is C upon m d minus again the same equation. So therefore we can write this equation as this is C upon m d minus K upon m minus omega square upon so C upon m d plus and minus, so it is the same equation as a plus b a minus b, so it is a square minus b square. So use the same equation, so it is a c square m square d square and minus K upon m minus omega square bracket square, okay, into sine omega t. And now we can cancel out d operator by replacing minus omega square. Okay, so f0 upon m replace this by minus omega square, so it is minus c square m square omega square minus K upon m minus omega square bracket square into sine omega t. Okay, so now we have removed the d operator from the denominator. Now the only d operator present, it is in the numerator. So just multiply sine omega t to this complete equation. So it is f0 upon m C upon m d sine omega t minus K upon m minus omega square sine omega t. And the denominator is minus c square omega square upon m square and minus k upon m minus omega square. Okay. So what is d sine omega t? So actually d sine omega t is nothing but the differentiation d by dt of sine omega t. Okay. So take the differentiation sine omega t. So it will become cos omega t. So differentiation of sine omega t, it is a cos omega t, and again differentiation of omega t, it is a omega. So we will get the term c upon m into omega cos omega t minus is k upon m minus omega square sine omega t, and this is minus c square omega square m square minus k upon m minus omega square bracket square. Okay, now we will try to simplify this equation. So here in the denominator, I have multiplied k minus m omega square upon m and whole bracket square. So I can write this k minus m omega square bracket square upon m square. Okay. Now from the denominator, you can take 1 upon m square common. Okay. And from the numerator, take 1 upon m common. So you can cancel out this m value. So this is 1 upon m, which is common from the numerator, upon 1 upon m square from the denominator. So finally, we will get this term as so this is m, okay, and then multiply by f0 upon m. So only remaining value is f0 after taking m square and m common. So it is a f0 and multiply by minus sign to numerator and denominator. So we can write the equation as, so this is cancelled. And after multiplying by negative sign, this is k minus m omega square sine omega t minus c omega cos omega t upon k minus m omega square bracket square minus, sorry, plus, because both are negative. So after multiplying by minus, both the terms will be positive. This is C omega square. Okay. Now our aim is we should have the equation for x, which is just a function of time. Okay. And it must be in the trigonometric function, either sine, cosine. So we will assume one right angle triangle with this as a hypotenuse. So assume this as a resultant R. This angle is phi, and this side, that is the adjacent side, it is a k minus m omega square, and the opposite side, this is a c omega. Okay. So now we will replace these values in this equation. So you can observe here from this right angle triangle, you can write these equations. R is equal to square root k minus m omega square bracket square plus c square omega square. Then adjacent side k minus m omega square, we can write this as r cos phi, and the opposite side is c omega, this is r sin phi. Now put these values in this equation of x particular integral. So we can simplify this equation. So this term in the denominator, it is nothing but the r square. So we can take r common. So finally we will get r in the denominator. Okay, so this equation is multiplied with f0. So it is f0 in the denominator. The value is r. If you cancel out the r value, Now, if you refer this equation, so this equation we can assume as an expansion of this equation, sine omega t minus phi. Okay. So if you expand this equation, then you will get the term. So this is sine A and B, sine A cos B minus cos A sine B. So you will get the same equation. Sine A means sine omega t, sine A cos B, so cos phi, minus cos A, that is a cos omega t, and sine B, that is a sine phi. Okay. So we can write this complete equation as, this is sine omega t minus phi. So this is complete the particular integral. Okay. And this f0 upon r, we can consider a constant value, because f0, it is the maximum value of the force and it is a constant value. R is nothing but this square root. Okay. So as k is constant, mass is constant, and the frequency of excitation is a constant. So this value will be constant. So we can assume this as a capital A. Okay. So I will explain what is meaning of this capital A. This is sine omega t minus phi. So this is our x particular integral. And this is the second half part of the complete solution. Okay. Now complete equation for the displacement. So this complete equation we can write x is equal to x complementary function plus x particular integral. So this is equal to a constant a1 e raised to, this is minus zeta plus square root zeta square minus 1 into omega nt plus a2 e raised to minus zeta minus square root zeta square minus 1 into omega nt plus the particular integral, which is a capital A sine omega t minus phi. Okay. So this part, this is the complementary function and this is the particular integral. So this is just a mathematical equation. But what is physical significance of this equation? So how we can visualize actual waveform during the force vibration? So therefore we should refer the displacement time graph from the damped vibration, because this complementary function, it is the same equation of the damped vibration. Okay. So just consider in this equation zeta value, which is a damping coefficient or damping ratio, not coefficient, it is a damping ratio. So zeta is greater than 1. So this case is overdamped system. So for the overdamped system, zeta to be greater than 1. If you plot the waveform for this equation, which is a displacement versus time, then you will observe the waveform like this. Okay. After a specific time interval, the displacement of the system, it will become 0. So this is displacement versus time. So what is the effect of this waveform, which is a sine omega t minus phi? Okay. So this is from the complementary function equation. So this waveform a sine omega t, so it is same equation as a simple harmonic motion, which is a sine omega t. Just changes, there is some phase lag phi. Okay, so forget about this phase lag. So it is the same equation a sine omega t, where a, capital A, it is the maximum value of the displacement. So we can have the waveform for a particular integral. If you plot this on the graph paper by displacement versus time, so it is the harmonic motion. Okay, so this maximum value of the displacement on both the sides, so it is nothing but the capital A from this equation. Okay, so as we are adding these two waveforms, so what is the combined effect? So if you superimpose both these waveforms, then the final waveform, so you will observe such type of waveform. Okay, after superimposition. That means if you add both the waveform and if you plot this complete equation on the displacement versus time, then you will observe such type of waveform. Okay, so this part, this is called as a transient. The transient meaning is there is an effect on the displacement for a specific interval with respect to time. Okay, and after this point, you can observe its amplitude is constant. So this is called as a steady state. Okay, so if you remove this part, that is the transient part, then remaining waveform, it will remain constant. That means its amplitude is constant with respect to time. Okay, so therefore, actually this transient part is only for a very few seconds. Okay, so after that transient part, system vibrates only with the particular integral equation. Okay, so therefore we can neglect this equation. That is the effect of complementary function in the force vibration. Okay, so complete equation X, by removing this complementary function, we can just write as a particular integral. And therefore, the solution of the force vibration which is X is written as X is equal to, it is only particular integral, and this is a sine omega t minus phi. So why we are not considering the complementary function? Because that complementary function effect, it will vanish after a specific time. Okay, and for remaining time duration, system only vibrates with the equation which is a particular integral. Okay, so this is your final equation for the force vibration. So if you refer the starting of this derivation, So our first aim was we should find out the equation for the displacement. Okay, so that equation we have just found out, x is equal to a sine omega t minus phi. And the second aim is what is the effect of changing the frequency of the force on the displacement. Okay. So we will try to find out that effect of changing frequency. So to study the effect various frequencies omega on the displacement x. So for that we should study this amplitude equation. So this is the amplitude of the force vibration. So we have this equation A is equal to, which is f0 upon r. Okay, because we have assumed this f0 upon r as a constant A. So this is the amplitude. Now put the value of r in this equation. So this is equal to f0 upon. So r value is square root. If you refer that triangle, it is a k minus m omega square bracket square plus c square omega square. So this is the capital A. Okay, so from this equation, just divide numerator and the denominator by this spring constant k. So we will get the equation A is equal to f0 upon k. And if you divide this square root, and if you take that k value in the square root, so it will become k square. And therefore, we should divide this by k square in the bracket. And this is also k square. Okay. So finally, we will get the equation 1 minus m omega square upon k bracket square plus c square omega square upon k square. Okay. Now this k upon m, we know this value. This is natural frequency for the spring mass system. So this is nothing but the omega n square. And this value, which is a c omega upon k. So we can simplify this c omega upon k. So this is c upon cc. Just divide and multiply by critical damping constant. So cc into omega upon k. So this is a damping ratio, which is a zeta. cc, this value is nothing but 2m into omega n and into omega upon k. So this is 2 zeta. Take this m in the denominator, so it will become k upon m, that is a omega n. So actually this is k upon m is nothing but omega n square. And finally, we will get equation as 2 zeta omega upon omega n. Okay. So we can replace this total value c omega upon k by this equation, which is a 2 zeta omega upon omega n. Now put these values in this equation. So A is equal to F0 upon K, and denominator is 1 minus, this is M omega square upon K, and C square omega square upon K square. So we have the equation K upon M is equal to omega N square, and C omega upon K, this is equal to 2 zeta omega upon omega N. So this take M in the denominator, so it will become K upon M, and that is nothing but omega N square. So 1 minus omega square upon omega N square bracket square plus C omega upon K is nothing but this complete value. So 2 zeta omega upon omega N bracket square. Okay, so this value is nothing but the amplitude. Now take this term F0 upon K on the left hand side. So right hand side, it will be just a function of external frequency omega and the damping factor zeta. So A upon F0 upon K, this is equal to 1 upon the square root 1 minus omega square omega N square bracket square plus 2 zeta omega upon omega N bracket square. Okay, so this ratio A upon F0 upon K, so this is called as a magnification factor. So with the help of magnification factor, we can study the effect of various forcing frequency on the displacement. Okay, and also we can study if we change the value of zeta, if zeta is underdamped or overdamped system, then what is the effect on the amplitude of the mass. So this is a dimensionless parameter, magnification factor. So now here we can assume this omega upon omega N as a small r, which is called as a frequency ratio. And we will write this complete equation in terms of this frequency ratio R. So A upon F0 upon K, this is equal to 1 upon the square root 1 minus R square bracket square plus 2 zeta R bracket square. Okay, and this F0 upon K, this is called as a static deformation. Or this is a zero frequency deformation. Okay, that means if this is a spring mass system, and if you supply only F0 force, which is a constant force, that means zero frequency force. It is not changing the direction. It is just an static force F0. Because of the F0, how much is the deformation of this spring? Is nothing but the X. Okay, or X static. And this X static, we can write it is F0 upon K, because F is equal to Kx. And therefore, it is called as a zero frequency deformation. And this value, it is written as a X static. So this complete ratio, which is a magnification factor, it is a upon x static. This is equal to 1 upon square root 1 minus r square bracket square plus 2 zeta r bracket square. Okay. So depending on this equation, we have a graph which is called as a magnification factor versus frequency ratio. So with the help of this graph, we can observe the effect of changing the frequency on this magnification factor. At the same time, what is the effect of this zeta parameter on this magnification factor or on this amplitude? Okay. So that we will study in the next lecture, the graph of magnification factor versus frequency ratio. So this complete equation, which is for the magnification factor, so it is a upon x static, it's function of omega, zeta, and omega n. So for a particular system, if you assume omega n as a constant, then it is just a function of two parameters, zeta and omega. So if you change any one parameter, either zeta or omega, you will get the different value of the amplitude or magnification factor.